Hello everybody. In this video, I'm going to go over some more about the gamma function. First, I want to note that the definition I gave, or one of the definitions, which involved the integral, and we had oops, that the gamma function was equal to the integral from 0 to infinity of x to the input minus 1 times e to the negative x dx. Now, this form is only acceptable when um, when the input z has a positive real part. So we would write the real part of z has to be greater than 0 for this integral to be evaluatable, however you say that word. Now, what that does not mean is that we can't use the gamma function on other inputs. So we saw, or I think in the last video I did the gamma of negative 1/2, and I may have done this, but we can't plug negative 1/2 into this integral and evaluate it because its real part, mainly negative 1/2, is not positive. But we can still evaluate it using the recursive relation that gamma of z plus 1 equals z times gamma of z. So I just wanted to point that out. Next order of business is the following integral. It's the integral from 0 to 1 of dx divided by the square root of negative natural log of x. Well, we have a square root and we have a negative, so first we're a little bit worried, but we notice that if x is from 0 to 1, then the natural log sort of goes like that. If this is the x-axis, it does not curve like that. But the point is, as x goes to 0, the natural log goes to negative infinity, and at x equals 1, the natural log is 0. So we have some weird bounds, but these bounds, we don't get any complex number craziness here. So probably the best idea would be to consider the substitution of u equaling negative natural log of x. So then du is equal to negative 1 over x dx. So dx equals negative x du. And here we have that x, if we just rearrange this equation, we get x is e to the negative u. So then dx is equal to negative e to the negative u du. Okay. And then our boundaries, so u, as x goes to 0, u will be the negative of negative infinity, which is infinity. So here we'll have infinity. And here we'll have 0. Well, we don't like going backwards, so we can use this negative here to flip the integral. So we have the integral from 0 to infinity. Now, so dx is e to the negative u du. And our square root of negative natural log of x, that is 1 over the square root of u. And that's u to the negative 1/2. Well, great. This is actually equal to the gamma function. As we see here, this is equal to the gamma of 1/2. And in the last video on factorials and the gamma function, I showed that this is in fact equal to square root of pi. So this definite integral is just equal to the square root of pi. And so I think that's going to be it for this video. Or I might go over one more example. Let's see. Okay, I think we're going to do one more problem. We have the following integral from 0 to 1, x to the 49th power times the natural log of x to the 50th power. So again, we're going to have to use some sort of substitution, and we're going to transform this into another gamma type integral. And in fact, we use the same substitution, u equals negative ln x, because it has the same properties. It takes 0 to 1 to 0 to infinity due to the negative and due to the properties of the natural log. So right off the bat, oh man, right off the bat we have 0 to infinity, and I just realized my cursor was a little, or my pen was a little bit light. So, and then we also have x is e to the negative u, and du is equal to negative dx over x. So we have negative x du equals dx. And so here, when we sub in dx, right, we can take this x and put it here. So we actually have x to the 50th. So, and then x becomes e to the negative u. So we have e to the negative 50u, apologies, times, and then natural log, well really we're plugging in negative natural log, but the even power makes it go away. So we get u to the 50th du. And we might be tempted to say, okay, this looks like, you know, gamma 50, or 50 factorial, which would be gamma 51, but we have a 50u here. We have to deal with that. And we can just deal with that with a simple substitution of v equals 50u. And what we get is 1 over 50. So we have to divide by 50 when we get our dv. But then also u, which is v over 50, will have v to the 50 divided by 50 to the 50. So if we factor that constant out, we get 1 over 50 to the 51, and then times our integral. That will give us, oh man, e to the negative v times v to the 50 times dv. Now we can use the gamma function, and we could say this is 50 factorial. So we get 50 factorial divided by 50 to the 51. And wow, this isn't simplified at all, but for our sakes it is. Or we could, I guess we could say, 49 factorial over 50 to the 50. But yeah, so there's often going to be, there are many tough integral problems that once you see, like once you use a substitution and get it into this kind of form, and then you can invoke um, the factorial or the gamma function. But often you have to do some workarounds. Like here, we had to get rid of this 50u, and but oftentimes, um, I mean, you're always gonna want 0 to infinity bounds so for the gamma function to work. Anyway, that's it, and I'll see you in the next video.